Let's think a little bit about what the results of our tests have shown us. One thing we saw was that all of our molecules were electrolytes. And so let's remind ourselves of what electrolytes are and are not. Non-electrolytes are soluble covalent molecular compounds. Anything that does not break up into a charged particle when it dissolves. So things which are soluble like sugar or miscible like most liquid alcohols, those things that don't split off and make any hydrogen ions in solution or any other ions in solution, those are non-electrolytes because those solutions are non-conductive. Anything in water that does break up into ions is an electrolyte. And the more ions you have in the solution, the more conductive the solution is. So generally things that we'll think about as electrolytes are, of course, our acids and bases, especially our strong acids and strong bases. So some really common strong acids you might recognize, hydrochloric acid, nitric acid, sulfuric acid. Those are all strong acids. And there are some strong bases to recognize. Things like the group 1 hydroxides, sodium hydroxide, potassium hydroxide, and barium hydroxide is also a strong base. Any soluble ionic compound is a strong electrolyte because when it dissociates into its separate ions. But there are also weak electrolytes, which also overlap with our weak acids and bases. And weak electrolytes do not break up and give up lots of ions when dissolved. So some really common examples of that are ammonia. When ammonia dissolves in water, it forms a small amount of ammonium hydroxide, and that is ionic, but most of the ammonia just remains as NH3. And acetic acid, one of our weak acids, that's vinegar. And acetic acid, only a very small amount of it breaks up to give us the acetate ion and H+. The vast majority of it stays together as an acetic acid molecule. So those are weak electrolytes. So as I mentioned, acids and bases are electrolytes. That means that, as we saw, our solutions of acids and bases do conduct electricity because they break up into those plus and minus ions. So the conductivity is a measure of the concentration of ions in solution. The more ions there are, the more conductive it is. And since we know strong electrolytes break up 100% into ions, and strong acids and bases break up 100% into their ions, then strong acids and bases are automatically strong electrolytes. And weak electrolytes do not break up 100% into ions. Most of them are much less than 5% dissociated into their ions. And that corresponds with our definition of a weak acid. So weak acids and weak bases are also weak electrolytes. So we can think about how that corresponds with what we saw of the conductivity of our strong and weak acids and bases. Even though they were all very close to the same molarity, the same concentration, we saw that our strong acids and bases had much greater conductivity than our weak acids and bases. And that's because they are strong electrolytes. Of course, acids and bases have a measurable pH because they break up into OH- and H+ ions. And again, the more the acid breaks up into H+ ions, the more the pH is going to change. And the more the base breaks up and gives me OH- ions, the higher the pH is going to be. So here's just a little visual. I like this Z diagram for relating the concentrations of H+ and OH- and the pH and the pOH. So if you look at this diagram, you can see here where I have a very large H+ concentration, my pH is very small because it is a negative log. So things which are acidic and have lots of H+ have very low pHs. And there really is still a little bit of OH minus floating around, and you can measure a pOH for this. Take the negative log of the OH minus concentration. But because the negative exponent will be like negative 11 or negative 12 or negative 13, the pOH is very large. So when pH is small, pOH is big. And of course, the sum of pH and pOH is 14. Then when I have a basic solution, as my pH is greater than 7, you can see I have lots of OH minus. I'm in the big Z opening over here. When I have lots and lots of OH minus, I only have a very tiny amount of H plus left. So my pH becomes very big. That means my pOH is very small. So it's a little bit counterintuitive. The smaller the pH, the more H plus there is. The smaller the pOH, the more OH minus there is. So the last thing I wanted to look at was to maybe do a little particulate map of this. What does it actually look like on a molecular scale? Because of course, as chemists, we're always thinking about the molecules. And so I have a little diagram here that kind of shows what's going on inside a beaker of a strong acid and a weak acid. And you can see that the strong acid has completely broken up. None of these HA molecules are still together. That's all H pluses and A minuses. They are dissociated from each other. They would be solvated by the water and floating around in the solution. And so you can see there are lots of ions and lots of H plus. So we have a very conductive solution with a lower pH. Even if I have the same number of molecules here, in a weak acid, only a very small percent of it will break up. In this case, this is technically 10%. Most acids are going to be even, weak acids are going to be even less than 10%. And so if I look at my weak acid here, move my face out of the way. If I look at my weak acid here, we can see the vast majority of these molecules stay together as HA. Only just one of them broke up to give me H plus and A minus. So there are many fewer ions in solution. The conductivity will be much lower. And since there's fewer H plus, and if we think about our Z diagram, fewer H's means that our pH is actually going to be higher. Even for the same molarity, a weak acid will have a higher pH than a strong acid. And you can think about these diagrams when you think about why.